In this video, I will be describing some of the different forms of concentration that we use in chemistry, and we'll finish our discussion with calculations on how to convert from one unit of concentration to another. In chemistry, most reactions, particularly biologically important ones, are done with components that are dissolved in water. Some of the terms that we will be using to describe concentrations and this dissolution of components are solvent. A solvent is the primary component that everything else is dissolved in. So in this example, that would be water. Solute or solutes are the minor components that are dissolved in the solvent. Solution refers to the combination of both the solvent and the solute taken together. We could talk about dilute solutions. Those are solutions where the concentration of the solute is low compared to the amount of solvent. On the other hand, we could have concentrated solutions. These are solutions where the concentration of the solute is high when compared to that of the solvent. Another subset are aqueous solutions. That is any solution where the solvent is water. An example of a solution would be a sodium chloride solution that contains 2.5 grams of the solute sodium chloride dissolved in 1 liter of the solvent being water. Different STEM fields use different forms of concentration. Concentration is essentially the amount of something per unit mass or volume that it is contained within. Depending on the situation, you'll use different units. In chemistry, the most common one is molarity, which is the number of moles of solute per liter of solution. It gets a symbol, capital M, and is determined as moles of the solute divided by liters of solution. Molality is a very similar unit, sometimes also used in chemistry, particularly in analytical chemistry. It is the number of moles of solute per kilogram of solvent. It has a symbol of M. Often the M will be more italicized so as to denote it as being different from meters. The units that make this up are moles of the solute per kilogram of solvent. Notice the difference between molarity and molality. Molarity is liters of solution, whereas the molality is kilograms of just the solvent. Then we also have mass fraction. This one is used primarily by those in the environmental field and engineers. Mass fraction is calculated as the mass of component per total mass. So mass fraction is the fraction having mass of the solute divided by the mass of the solution. So again, solution is a combination of both the solute and the solvent. Mass percent, also sometimes called percent by mass, is the mass fraction times 100 to convert it into a percent. Last, we have parts per thousand, million, billion, trillion, which is very similar to the concept of mass percent or mass fraction. Essentially, parts per million, as an example, is your mass fraction times a million, as opposed to times 100, which was the case for mass percent. For the other forms of parts per, such as parts per billion, you would multiply the mass fraction by 1 billion. Let's now look at some problems relating to concentration and the interconversion between different concentration units. Problem 1. What mass of sodium chloride should you add to 1.20 liters of water to make a 0.50 molar, that's moles per liter, aqueous solution? What would the molality and mass percent of the solution be? We're going to assume that the volume doesn't change and that the density of water is 0.9806 grams per milliliter. Because the volume doesn't change, the volume of the water that we are putting the sodium chloride into is going to be the same as the volume of the solution. So the way that we're going to tackle this is to do the first problem first. We're going to figure out the mass of sodium chloride that we should add to 1.20 liters of water. So we can take 0.50 moles of NaCl per liter of solution, multiply this by our volume of solution, 1.20 liters. This will give us our number of moles of sodium chloride. This is 0.60 moles of NaCl. We can then take our 0.60 moles of NaCl and multiply that by our molecular weight, putting grams on top. Grams of NaCl on top and moles of NaCl on bottom. 1 mole of sodium chloride is 58.443 grams. Moles of sodium chloride cancel out. This gives us grams of sodium chloride. Plugging this into your calculator, you'll get 35.0658 grams of sodium chloride. In terms of significant figures, our initial moles here had 2 significant figures from our initial concentration, which only has 2. So in the second calculation, the 0.60 moles of sodium chloride times our molecular weight, the first value has 2 sig figs, the molecular weight has 5, and so our end answer will have 2 significant figures. So that will come out to be 35 grams of NaCl. Okay, the second part of the question asks, what would the molality and mass percent of the solution be? Let's work out our molality first. And again, molality is moles. In this case, it would be moles of sodium chloride per kilogram of our solvent, which in this case is water. So we've already figured out the number of moles of sodium chloride. We did that in the first part. Now what we need is the kilograms of water. So for the kilograms of water, what we're going to do is take our volume and work with our density to figure out the mass. So we'll take 1.20 liters of water, multiply that by 0.9806 grams per 1 mil. Our volumes don't quite cancel out. We have liters and milliliters. So what we'll need to do is do an interconversion. So we're going to put liters on bottom, milliliters on top. 1 milliliter is 10 to the negative third liters. Our liters here cancel out liters there. Milliliters cancel out milliliters. So if we did this calculation at this point, we would have our grams of water, which work out to be 1176.72 grams of water. To convert this into kilograms, we just shift the decimal place to the left by 3, giving us 1.17672 kilograms. In terms of significant figures, our first value, the liters, has 3. Our density has 4. The conversion between milliliters and liters doesn't come into play, so our end answer will have 3 significant figures. Okay, plugging it into our molality, that is moles of sodium chloride per kilogram. We then just plug in our values. So 0.60 moles of sodium chloride divided by our mass in kilograms. So that's 1.1767. We always want to keep a couple extra digits to prevent a rounding error. This is kilograms of water. That gives us a molality of 0.509901 molal. In terms of significant figures, our top value has two significant figures. The value in the denominator has 3, so our end answer will have 2. So this comes out to be 0.51 molal. Again, that's a more italicized m to denote that it's different from meters, which is also a lowercase m. The last part is figuring out our mass percent. So mass percent, or percent by mass, is the ratio of the mass of our solute. So that would be mass So that would be mass of NaCl divided by our mass. Okay, this is mass of sodium chloride divided by the mass of our solution. The mass of the solution is everything. That's the solute and the solvent. So we could think about this as mass of our NaCl divided by the mass of water plus the mass of the NaCl. So this would be equal to 35.07. We'll just round our value, keeping a couple extra significant figures, divided by, this is grams of NaCl, divided by 1176.7 grams, this is water, plus 35.07 grams of NaCl. And then we multiply all this by 100% to convert it into a percent. Plugging it into your calculator, you'll get the percent mass is equal to 2.89373%. In terms of significant figures, our top value had 2. Our bottom value, well, this part has 2. This one is here. In the denominator, we're going to end up with something that has 3 significant figures, right? Because for significant figures, when you're doing addition subtraction, it's the one that has the least significant decimal place, so it will be good only to the tens place. So on the top, we have 2 sig figs. On the bottom, we're going to end up with 3. So our end answer will only have 2 significant figures, so this comes out to be 2.9%. So our answers for the first part, 35 grams of sodium chloride. For the second part, the molality would be 0.51. And the last part, the mass percent, or percent by mass, would be 2.9%. For the second problem, a student dissolves 25.5 grams of potassium bromide in enough water to make 1.75 liters of solution. What is the molarity, that's moles per liter, of the solution? Assuming the density of the solution is 1.100 grams per mil, calculate the molality and mass percent. So again, we're going to do the first part first. Right? We're going to find the molarity of the solution. So molarity is moles per liter. Molarity equals moles, and this is moles of our solute, so moles of KBr per liter of solution. So the first thing we want to do is figure out our moles of potassium bromide, and then, well, we already have our liters of solution. So to find moles of potassium bromide, moles of KBr, that would be equal, we can take our mass, 25.5 grams of potassium bromide. We can multiply this by our molecular weight, putting grams on bottom, moles on top. 1 mole of KBr is equal to 119.002 grams of KBr. Our masses of KBr cancel out, leaving us with moles of potassium bromide. If you plug this into your calculator, you should get 0.214282 moles of potassium bromide. In terms of significant figures, our first value, the 25.5, has 3 sig figs. Our molecular weight has 6, and so the end answer is going to have 3 significant figures. So we now have our top value for molarity. To get our bottom value, it's already present in our question, the 1.75 liters. So our molarity is equal to our 0.214282 moles of KBr. We're going to take this, divide it by our volume of solution, 1.75 liters of solution. This will give 0.1224469 molar KBr. In terms of significant figures, our top value has 3, our bottom value has 3, and so our end answer is also going to have 3. So our answer would be 0.122 molar KBr, or moles per liter. The next part that we're going to work out is our molality. Molality is equal to our moles of our solute, or KBr, per mass in kilograms of our solvent. The difficulty that we're going to have is that our volume is for our solution and our density is for the solution, not the solvent. So our total mass, or the mass of our solution, that is equal to the mass of the solute plus the mass of the solvent. Rearranging this to solve for the mass of the solvent, the mass of our solvent, which is what we're after, is equal to the mass of our solution minus the mass that comes from the solute, which in this case would be our potassium bromide. So if we find the mass of our solution, we can then subtract the mass of the solute, which was given in the problem, and that will give us the mass of the solvent. So the mass of our solution would be equal to 1.75 liters of our solution multiplied by its density, grams on top, milliliters on bottom, 1.100 grams per 1 mil. In order to cancel out our volume, we need to convert our milliliters to liters. So we're going to put milliliters on top, liters on bottom. 1 milliliter is 10 to the negative third liters. Liters of solution cancel out, milliliters cancels out milliliters, so we now have grams of our solution. If we plug this into our calculator, we'll have grams of our solution, but we're after kilograms. So we are going to need to do one last conversion, convert out of grams into kilograms. 1 kilogram is 10 to the third grams. Our grams cancel out. Plugging this into your calculator, you'll get 1.925 kilograms, and this is the solution. Okay, now to find the mass of the solvent, that is equal to the mass of the solution minus the mass of the solute. So that would be 1.925 kilograms of solution minus our initial mass of potassium bromide converted into kilograms. To do that, we just shift the decimal place 3 units or 3 spots to the left. So that would be 0.0 0.255 kilograms. And this is our KBR. In terms of significant figures for our mass of the solution, in our previous step we had 1.75, which has 3 significant figures. Our density has 4. Our 2 unit conversions, those do not come into play, so our value would have 3 significant figures. Okay, so this is significant to the 100th place. So when we do our subtraction here, we get an answer of 1.8995 kilograms for our solvent, which in this case is going to be water. In terms of significant figures, our value is good to the 100th place, which would be right here. So if we were interested in the mass of the water alone, it would be 1.90, but because we're going to be using this for sequential calculations, we would keep track of all this stuff. Clearing up some space to continue the calculation. To figure out the molality, we can now fill in our values. We have the moles of potassium bromide from before at 0.214282 moles of KBr, and we can now divide this by the kilograms of solvent that we just determined, which was 1.8995 kilograms of water, and that was good to 3 significant figures, and the top value is also good to 3 significant figures. Plugging this into the calculator, you get 0.112810 molal, which is good to 3 significant figures, which would turn into, if we round it, 0.113 molal of potassium bromide. To find the last part, we're going to look at our mass percent. So our mass percent is equal to the mass of KBr divided by the mass of our solution. We had previously, when we were working out the molality, as part of our interim step, we had worked out the mass of the solution, which came out to be 1.925 kilograms, and the mass of the potassium bromide was 25.5 grams. They need to be in the same unit, so we can convert our kilograms and grams. We'll put kilograms on top, grams on bottom. 1 kilogram is 10 to the 3rd grams. And then multiply by 100 to convert it into a percent, and you end up with 1.3247%, which in terms of significant figures, our top value has 3, the bottom value had also 3. So our end answer will have 3 significant figures. So that would be 1.32%. So our answers to this question, the first one, what is the molarity, was here, 0.122 molar. The molality was here, 0.113 molal for our potassium bromide solution. And then the last part, our percent by mass, will be 1.32%.